To lesson 5.1 or chapter 5, trigonometric proofs. We're going to begin this with the basic trigonometric identities. These are identities that you will need to memorize. We will add to them throughout the unit. But in the initial lesson, we're going to cover these identities and you're going to try to use them with properties that you know for adding and subtracting fractions, multiplying and dividing fractions, simplifying rational expressions, like you learned in Algebra 2 and Algebra 1, along with the trig identities to do trigonometric proofs. We begin with the reciprocal identities because these are the most basic, the ones that you should be pretty familiar with. That's just the reciprocal of sine. The reciprocal of sine is cosecant. The reciprocal of cosecant is sine. Cosine, the reciprocal is secant. And secant, the reciprocal, is cosine. So if you know one, then you'll know the ratio of the other one is just 1. If you know sine, then the relation for cosecant is 1 over cosecant. Whatever the decimal value is of this to the reciprocal to get the is equivalent to 1 over its reciprocal. Tangent, we have 1 over cotangent. Because if I do 1 over tangent, that is the same as cotangent. If you need to see some examples of this, look to your unit circle. We have at pi over 4 on the unit circle, we have that tangent is 1. And cotangent, the reciprocal of 1, is also 1. However, we look at the unit circle at pi over 6, and pi over 3, and you see a difference there. Okay? Same thing with sine. When sine of pi over 4 is square root of 2 over 2, cosecant of pi over 4 is 2 over square roots of 2. Okay? Or another way to put that is 1 over sine of pi over 4, because that would be 1 over square roots of 2 over 2. Quotient identities. We've already discussed tangent on the unit circle is y divided by x. And remember, on our unit circle, we have cosine theta, sine theta. So tangent is y divided by x, which is rise over run on our unit circle. And so it is equivalent to sine divided by cosine. Whereas cotangent is equivalent to cosine divided by sine. So these are identities that we should already be somewhat familiar with. These, definitely familiar with these, the reciprocal trig functions of sine, cosine, and tangent. Reciprocal trig functions of cosecant, secant, and cotangent. We also have our Pythagorean identities. So we're going to go back to deriving the first one. Okay? We have, in the circle, we have y, which is sine of x, or sine of theta. We have our angle theta. We have x, which is cosine of theta. And we have the radius. In this circle, we have, if you were just looking at this as a right triangle, a squared plus b squared equals c squared. So I have, using a squared plus b squared equals c squared, I would get x squared plus, actually I wanted to do y first, I don't know why I did that, y squared, I'll treat this one as a, y squared plus x squared equals r squared. Well, y is sine. So this is sine theta, sine squared theta, or sine theta squared, plus cosine squared theta equals r squared. And in our unit circle, remember that r equals 1 unit for our unit circle. So this is our equation. Sine squared plus cosine squared equals 1. That is our very first trigonometric identity. I kind of did both of these in one before. I used to do it a little bit differently, where I'd label this x and y and r, and this cosine and sine and r to show the same thing. So our very first identity is that sine squared theta plus cosine squared theta equals 1. Now a quick note about sine squared theta and any trig function squared. It doesn't matter where you put the squared because we have to do the sine of theta and then square it. So I can put the squared on the sine, I can put the squared on the whole thing, I can put the whole thing in parentheses and then put the square on it. Those are all equivalent. It is not like where we have expressions like x times y and we have to make sure that that exponent goes to both factors. It's not like that. This whole thing is sine of theta and it's being squared. Sine of theta, the whole thing's being squared. Sine of theta, the whole thing's being squared. And so that's true for any trig function. It doesn't matter where you put the squared. You can put it between theta and the trig. You can put it after theta, or you could put the trig function and theta together with a squared on the outside. All of those are equivalent. Now, so we have our original function using our original Pythagorean identity. This is the first Pythagorean identity that we've looked at. When the radius is 1, we have sine squared plus cosine squared equals 1 squared, or 1, because a squared plus b squared equals 1 squared. Now, if I want to be tricky here, I could divide everything from the first one by cosine squared. And so in doing that, I'd have sine squared theta over cosine squared theta plus cosine squared theta over cosine squared theta equals 1 over cosine squared theta. Using our reciprocal identities, right? I've got sine squared over cosine squared. So that's really like sine over cosine, the whole thing squared. That is tangent squared theta. Because remember, tangent is sine over cosine, and that's what I have here, sine over cosine, and they're squared. They both have to be squared for this to work. Then here, cosine squared divided by cosine squared is 1. And 1 divided by cosine squared is the reciprocal. 1 over cosine is the reciprocal of secant, but it's squared. So this is secant squared. This is our second Pythagorean identity. Our third Pythagorean identity also takes the very first one, but this time instead of dividing by cosine squared, I'm going to divide everything by sine squared. So I will have sine squared theta over sine squared theta plus cosine squared theta over sine squared theta equals 1 over sine squared theta, because I've taken this original Pythagorean identity, divided every single term in the equation by sine squared. Sine squared divided by itself is 1. Cosine over sine is cotangent, but they're both squared, so it's cotangent squared theta. And 1 over sine squared, 1 over sine is cosecant, so this is cosecant squared. So now we have our 3 Pythagorean identities. There are various ways that we can rearrange these. I can make these add to 1. I could take one of them away from 1, getting sine squared by itself, or take the sine squared away from 1, getting the cosine squared by itself. We're going to look at rewriting these 3 different ways on the next page. But these are the Pythagorean identities that we need to memorize. We can manipulate them to get other identities, such as sine squared equals 1 minus cosine squared, but they come back from this original first one. And these 2 were generated from this first one. So yes, you should already have memorized the reciprocal identities. If you weren't already familiar, you now know the quotient identities. And now we have 3 Pythagorean identities coming directly from Pythagorean's theorem with the unit circle. We're going to take these identities and we're going to manipulate them, because when we're doing trig proofs, they're not always going to be so obvious to us. So they might turn up as a different expression or a different way of writing the equation. So remembering that our first one was sine squared plus cosine squared, these should have thetas, equal 1. If I wanted to, I could solve for sine. I could get sine squared by itself by subtracting cosine squared from 1. Similarly, I could take the original equation and I could subtract sine squared to get cosine squared by itself. Take a moment to pause the video and see if you can do this for functions for the second and third function after you've written them down. So remembering that this one is tangent squared theta plus 1 equals secant squared theta. I'm just checking what color I put these in. And 1 plus cotangent squared theta equals cosecant squared theta. If you can pause the video for a moment and manipulate those to solve for tangent squared by itself and secant squared by, well, 1 by itself and cotangent squared by itself. Welcome back. Here are the trig functions that you should have come up with. When solving to get 1 by itself, you'd had to subtract tangent squared theta. When solving to get tangent squared theta by itself, you had to subtract 1. When solving to get 1 by itself, you had to subtract cotangent squared theta. And when solving to get cotangent squared by itself, you had to subtract 1. So there are actually 9. 3 Pythagorean theorems can be represented in 9 different ways if we're looking at this. So we at least want to be familiar with at least one of them. So if I know this and during a trig proof or something that I'm trying to solve later, I see a sine squared, I can remember this formula and I might have to manipulate it to get sine squared by itself. But if I have this one memorized, I can always figure out these other 2 to help me solve a problem. Some people just memorize all 9 of them, but there are other things we're going to have to memorize. So once again, these are the ones that we derived first. This one I normally memorize. I normally memorize these top 3, but some people choose to memorize the ones that are equal to 1. And that way they can, if they memorize those 3, they can always figure out the other one. Just don't get your signs wrong. Here they all have plus signs, so if I memorize the top ones, I'm good. We also have something called the Cofunction Identities. So again, on these, you can memorize the 3 of them and generate the rest as needed, or memorize all 9. Cofunction Identities. Conceptually, I want you to see what we have here. Here's a 60-degree angle, here's a 30-degree angle, and 90-degree angle. And in this triangle, we remember have side lengths of 1, 2, and long leg square roots of 3. The sine of 60 is the square root of 3 over 2. The cosine of 30 is also the square root of 3 over 2. But 30 is really 90 minus 60 because those angles are complements. Complementary angles give us our cofunction identities. So sine of pi over 3 is 60 degrees. That's the same thing. Sine of pi over 6 is 30 degrees, and that gives us the same thing. So before we're looking in degrees for the 30, 60, 90 triangle that you're familiar with, this is the same exact thing. It's just expressed in radians. So it's important to note that complementary angles A and B, the sine of A will equal the cosine of B. Angle B, this is the key right here, is pi over 2 minus angle A. 90 minus the 60, those are our complementary. Complementary in terms of radians, the 2 angles add up to pi over 2, half pi. So angle B equals pi over 2 minus A. So this is how we define our cofunction identities. Let me see what colors I had. Teal? Okay. So sine is going to be equal to cosine of pi over 2 minus theta, because these are complements. Cosine, therefore, is equal to sine of pi over 2 minus theta. We also have secant and cosecant. secant is equal to cosecant of pi over 2 minus theta. Cosecant is equal to secant of pi over 2 minus theta. And even tangent, because if you look at the tangent function, the tangent of 60 degrees is square root of 3 over 1. The tangent of 30, or the tangent of 30 degrees is 1 over square root of 3, so those are not going to work out the way I wanted them to. These ones do, for certain. We'll talk more about this when I return to class. All right, so we have recall even versus odd functions. We've even reviewed this a few times this year. Remember, even functions have symmetry with the y-axis, and odd functions have rotational symmetry. So when we look at sine, we've talked about this before, because of the nature of sine, I could rotate this around and it would fall on itself. So sine is an even function because it has symmetry with respect to the y-axis. We talked about this also when we started graphing, that cosine, oh, not even, I said rotational, so it's because sine has rotational symmetry, it's odd. Cosine is the one that has symmetry with the y-axis, so that one's even. Tangent, remember, and this is the parent function before any transformations occur. Tangent's function, parent function, we didn't really talk about it when we did tangent, but it also has rotational symmetry. So it is also not even. It has rotational symmetry, so it is odd. Rotational symmetry is odd. Y-axis symmetry is even. So cosine is the only one that has y-axis symmetry. It's the only one of these that is even. This leads us to yet another identity. Because if you remember, for these functions, for even, f of the opposite of x is the same as f of x, right? If I put in pi over 2 for cosine, if I put in pi over 2 for cosine, it's the same output as if I put in negative pi over 2 into the function. But for sine, if I put in pi over 2, then if I put in the opposite value, negative pi over 2, I get the opposite output. Instead of going up 1, it goes down 1. So that leads us to the following. Because sine and its reciprocal are odd, do that in the right color, yes, and tangent and its reciprocal are odd, and cosine and secant are even, when you plug in a negative angle into cosine or into secant, you're going to get the same thing as if you plugged in the original angle, the positive angle, and vice versa. Plug in a positive, okay, same thing. You're going to get the positive output, same as a positive. Plug in the negative angle, you get the positive. For sine and cosecant and tangent and cotangent, though, if you put that negative in, you get the opposite output. The opposite output. We're going to be using these to prove trigonometric functions. So I'm just going to give a couple of brief examples in the next clip that use these identities to do some basic proofs to get you started and give you some examples before you start working on this on your own.